Hello everyone. Today I will present our work entitled EchoLLM, an augmented acoustic eavesdropping attack on band conduction headphones with mmWave radar. This research focuses on the privacy risks of band conduction headphones and introduces a novel eavesdropping attack that leverages mmWave radar and large language model. In recent years, the band conduction headphone market has grown rapidly. Compared with traditional headphones, they allow open-ear usage and are suitable for sports. However, they also raise potential privacy concerns, since bone conduction headphones transmit sound through vibrations. Their audio output can be inadvertently exposed, potentially leaking sensitive information such as passwords, work details, or private conversations. Acoustic eavesdropping attacks can be classified into two categories: internal and external. Internal attacks rely on the device itself, such as an IMU embedded inside a smartphone. An attacker may gain access through a malicious application or permission vulnerability. However, such attacks are limited as they require access to the victim's device and often rely on the victim to install malware. External attacks are much more insidious. Previous studies have shown that an attacker can reconstruct speech using lasers reflected from surfaces, vibrations from light bulbs or tables, or even Wi-Fi signals. Although these methods do not rely on the victim device, they face the challenge of balancing accuracy and robustness, and often have high cost or poor concealment. Our work follows the external attack paradigm by introducing mmWave radar. It has the advantages of low cost, high sensitivity, and easy integration, which can overcome the limitations of existing methods and achieve more precious eavesdropping. The previous eavesdropping attacks based on mmWave radar almost follow the following process, including sound source signal acquisition, vibration signal extraction, speech enhancement, and evaluation of eavesdropping effect. However, existing acoustic eavesdropping attacks still suffer from two key limitations. First, they usually assume that the target audio belongs to predefined categories, such as letters or digits, and attackers must have prior knowledge of these categories. Second, they rely on stable reflective surfaces and cannot handle context-dependent natural speech. Moreover, they lack the capability of multi-modal data integration. As a result, their applicability in real-world scenarios remains limited. In addition, we also find that past evaluation metrics focus on audio itself, but perform poorly on downstream tasks such as speech recognition, where world error rate WER is still high under the premise of good STOI and PSNR. So, we need a novel approach to break through predefined content categories and applicability constraints, achieving high WER eavesdropping attacks. We consider the threat model where the attacker and the victim are in the same physical scenario and the victim is talking to colleague using a band conduction headphone. In such a scenario, we first expect to achieve context-aware eavesdropping by exploiting semantic dependencies in the dialogue context. Second, considering the contextual dialogue in the scenario, where the speech signals are not in the same model, we expect a more robust attack by multi-modal fusion, where the mmWave radar signals targeting the victim's earphones and microphone signals directed at the victim themselves. Next, we want to implement covert and low-cost attacks, and highly integrated commercial mmWave radars meet this need. Finally, considering the complex scene and user movement, it is necessary to design attacks with target awareness and motion resilience to make them highly applicable in practical applications. Our system EchoLLM will proceed as follows. First, victim caller used a band conduction headphone to talk to colleague. Next, the attacker uses a mmWave radar and a wireless microphone to collect band conduction headphone signals and the caller's voice. ADC raw data and recording fields are absent. For ADC raw data, we design targeted vibration extraction and audio enhancement. Audio enhancement consists of two parts: background reflection reduction and motion calibration. Finally, the data of the two modalities were input into LLM, a large language model-based speech-to-text model, and the final output of caller and colleague dialogue text was absent. Next, I will introduce the details of each part in detail. In the vibration signal extraction, we need to distinguish the victim from other objects such as tables, chairs, and so on in the radar view. We first narrow the suspicious target range by setting the threshold range of speed. Then, observing that the spectrogram is clearly distinguished from the case without speech in the presence of speech activity, we use the CNN-based voice activity detection model EchoWave to find the audio activity and its timestamp in the candidate regions. For regions with audio activity, we find the successive range bins all have distinct voice activity. Therefore, we choose the range bin with the largest SNR as the extraction location. Finally, we use the relationship between the phase change and the displacement change to restore the time series of the vibration signal. After obtaining the vibration signal, we need to perform a series of enhancements to this signal. First of all, since the reflected signal includes the signal reflected by other sources in addition to the target, we need to perform background reflection reduction. We adopted the circle fitting method of Mobicom 2020 to eliminate the reflection of the rest of the background. Next, we observe that the signal contains a lot of spikes. We speculate that the causes are caused by inter-frame discontinuous, segment-wise fitting artifacts, and cross-frame localization instability. We can clearly see the spike in the time amplitude plot. We propose spike-free, an algorithm for spike elimination that is based on an LSTM model to interpolate the missing values and flatten phi t via averaging and offset calibration. The final result is showing the figure, which has a good effect on removing the spike. Next, we also need to reduce the influence of the victim's head movement on the signal. As shown in the figure, the victim's head movements still add low-frequency components to the signal. We first used a moving average filter to obtain the low-frequency motion time series, and then performed the difference to obtain the final audio vibration signal. The figure shows the movement of the low-frequency part as well as the removal. Next, I will introduce the context-aware multimodal ASR, LASR. It consists of 5 parts. In the multimodal input part, we adopt a two-stage fine-tuning strategy to input the synthesized conversational audios and self-collected realistic data. Next, embedding extraction is performed on the data of each modality respectively. The embedding layer can be chosen from options such as VGG, Hubert, Wave2Vec, and so on. In the embedding alignment section, we concatenate the embedding vectors of each modality and insert the BOS at segmentation to facilitate the subsequent evaluation. Concatenated vectors are fed into large language models such as BART, Whisper, Speech-T5, and so on. We use the widely adopted autoregressive cross-entropy loss to train LASR, which measures the difference between the predicted probability distribution of the next token and the actual tokens in the training data. The final output text will be split into color text and quality text according to BOS, and only the WER of the quality part will be calculated for evaluation. In the following, I will describe our experimental setup and the results. Our hardware cost total $930, including the millimeter wave radar and the wireless microphone. We then evaluated our system by varying the volume, distance, and angle. The experimental results are shown in the figure. It can be seen that WR increases with the increase of volume. The increase of distance leads to the decrease of WR. However, the change of angle has little effect on WR. We also tested the effect on different action on the eavesdropping effect. It can be seen that the static state has the lowest WR, while the motion of the human body makes the WR increase. In the ablation experiment, we explored the influence of context and speech enhancement model on the eavesdropping effect. It can be seen that the context greatly enhances attack performance as well as reflection reduction and motion calibration enhance the attack efficiency. We also tested the robustness of the attack, as shown in the figure. We selected 4 different environments and 3 different types of BCH for testing. Experimental results show that EchoLLM is robust to different noises, different environments, and different BCH types. In addition, we conduct experiments on multilingual robustness, user diversity, headset diversity, attack effect comparison, numerical data influence, and sensitive information interference, and the results are shown in the table. As can be seen from the data results, EchoLLM has achieved the state-of-art performance. In conclusion, we propose EchoLLM, the first mmWave-based eavesdropping attack tailored for coin-sized band conduction headphones. Second, we develop LASR, a novel context-aware multimodal ASR framework. Thank you for listening.